Okay, so like I said, we have R, and we shall be using the FEAR package and then the benchmarking package. Other softwares are Max DEA. When you're doing a practical work, you use the Max DEA, which we have. EMS is a bit old, but it's very good for productivity. LIMDEP combines both parametric and non-parametric. Lindo and Lingo are mathematical programming softwares. Warwick DEA is very old, but it's quite useful to give you some specifics. DA Frontier is by Zoo and it's quite good. At least no three of them. Okay. But basically, we are going to use R and it does most of the thing. So the first thing I want us to do is to just learn some few basics of matrices that you have to understand in R. Please, have you typed these commands already? Have you typed this very command that I've highlighted?
Yes, Doc.
Okay. So type that command and run that command. I'm going to see if I can use, this section here in R to be able to do a similar thing for you. So look at the top. I have typed the same commands. Okay. So that command is a matrix. And when you look at this matrix, they are all put together. Okay. And so you use this command for n row to indicate the number of rows. And then this becomes the number of columns. So you are saying that with this data, the number of rows, so 1, 2, 3. Okay, you want the rows to be what? 3 rows. So the first one, okay, will be 1 row. The next one will be 2 rows. The next one will be 3 rows. So when you run it, okay, I've run it. And so I want you to do the same thing. When you run this command, and then you just highlight the results. Look at the results down here. You can see that when I highlighted B and then Control Enter, you are able to see the results. And you can see that it's showing 3 rows. Okay, 3 rows. One is this. The second row is that. The third row is that. It's showing them. Okay. So this is when you have the data actually, all mixed up. Okay. However, go to your second command. Go to your second command. Okay, when you check your second command, and let me just go in there to show you. This is the second command, C. So C is also a matrix. How many rows does it have?
Yeah. 3 rows and 1 column.
3 rows and then 1 column. So once again, when you now type that into R, which I know you have, and you run it, if you go and tell how to show you the result, you see that it is 3 rows. The first one is row 1, which has 7, row 2, which has 4, and then row 3, which has 2. And that's an individual matrix. But you can combine these matrices. You can combine the 2 matrices. So we're going to do a command called cbind. Cbind the. So if you look at my command number 3, I've written cbind into bracket capital B, capital C. So what I'm trying to tell R is to combine them. So I'm combining the 2 matrices. Now, how do you combine them? Let's run that, and you can see. Okay. So if you look at the first command, it was 2, 1, 4, 5, 3, 7. Now you have 2, 1, 7. The 7 has been added. So you have created a new thing. We could have called it something like D. Okay. And then now you have a new kind of a data right there. So that is the importance of that. Now you can now create another matrix. Okay. This command that we just used was a column bind. So it means that the next one should be on the column. Now let's create another command, which is your D. Another command, which is your D. Okay. So go to your D in your, okay, so in my, you have column, my command number 4. Okay, that's D. And D is made up of observations of 6 and 2. And this is 1 row and then 2 columns. So if I run that, 1 row, 2 columns means that they are all going to be horizontal. Okay, that's a 6 and 2. Now, I can use a row bind instead of C bind. I can use R bind. C bind is when you are column binding the thing. So I can use R bind when you are row binding, so that I row bind B and D. So I type row bind B. So I'll take this B and then D. Okay. Now, if you can remember B is 214537. And now D is 62. And I am row binding them. So it will be added as one of the rows. Okay. So let's run that. And when you look at it down here, you can see that the D has been added as one of the rows. So that's what we mean by row binding and column binding. Do you get it?
Yes, Doc.
Yes, Doc.
Okay. Now, the next thing to do is to understand what a data frame is. What is a data frame? What is a data frame? Okay, and that's the next thing we want to look at. Now, a data frame combines matrices and lists, their features together. Okay, now there's one particular data frame which is inside the R already when you installed it. We're going to deal with that data frame. And when we talk about data frame, it's simply a data set, just as you normally have it in your thesis, in your anything. Okay, it has many columns and then many rows, and it has names of the items. Now, the matrix doesn't usually have names. So talking about data frame, let's just go and then show you one data frame by running this command for plant growth. So I'm doing that plant growth here. And it's already in the memory of R. So once you run it, it will show down here in the console. Okay, so look down here. You will see that it's a data set which is made up of weights, which are numerical variables, and then group, which are categorical or string variables. So you can see that the groups, you have CTRL, TRTL, and then TRT2. So TRT1, CTR1, and then it's made up of just 30 observations. So this is a typical example of a data set. A data set. Okay. So now let's go and look at our data set. Guys, you know that this is a data set we have been dealing with all this while. Forget about the last two columns. Do you realize that this data set we have been dealing with that? Do you guys remember? Do you remember that this is a data set?
Yes, sir.
Okay. So what we are going to do now is we are going to now put this data set into Excel. We already have it. You all have it in your Excel.
Yes, Doc.
Yes, Doc.
So copy it and then let's go to the Excel. Copy it and then let's go to the Excel. Now, there are some few packages you want to install first. Okay. Package number one is benchmarking. Have you installed benchmarking?
Yes, Doc.
Good. If you have a question, just ask me. Don't worry. So,
Doc, please, I have a question.
Go ahead.
Please, the plant growth. When I inputted it, the data didn't show.
The data did not show, right?
Yes, Doc.
Okay, probably sometime it might be due to the version you are using. It might be due to the version you are using. Sometimes you may have to install a certain package for that to happen. But don't worry, at least you get the idea, don't you?
Yeah, yes, Doc, I do. Yeah.
Yeah, Morrison.
All right, Doc, so please, I was also saying my own didn't show.
Okay. Whose own showed?
All right, thank
Doc, my own showed.
Yeah, mine showed.
Okay. So I guess you can just find it. But it doesn't matter much. It's just a way to show you what a data set is all about. Okay. So now I want us to, you have already installed the R, the benchmarking. You have already installed it. So since you've already installed a benchmarking, what you want to do now is to go to your R and just type require benchmarking. Sometimes you can simply do library benchmarking, it's the same thing. Now, this is simply a way to evoke. Now, that's if you install the benchmarking. If you haven't installed it, you have to install it first. How do you install it first? It's just a matter of going to your packages and going to install, and then click benchmarking, boom, and you see it showing. And once it shows, you click install and install. Now, for you to know that you have it, just look in the search of the packages and type bench, and you see that straight away to come. And in my case, that's the one is coming. The version is there. Okay, that's the version. Sometimes if you want to update, you can update any particular thing you want to, update. Okay, so you can use the update to update. Okay, so run the benchmarking. Okay, run it. And then let it show. Now, in the bottom, you will see that require benchmarking is showing. Okay, so that means that we are ready to do our efficiency and productivity analysis. So the first thing you want to do is to bring the data into R. So go to your Excel. Go to your Excel. And just as you see it here, copy the data into R. Copy the data into R. I'm trying to see whether, I have it. You all know how to run the data, but the command we are going to use to run the data, call the data FAM1, F-A-M. It's just a way to shorten it for family, FAM1. I'm trying to see if I can show you mine in Excel. I'm trying to see if I can show you mine in Excel. Okay, so let me show you mine in Excel. Okay, so guys, you see my Excel?
Not yet, Doc.
You see it?
No, please.
I've actually highlighted it.
Okay. It's showing now.
Okay. So this is the data set. Okay. And the first column is the name of the DMU. The second column is for output. And the other two are the X1 and the X2 as input. I'm sure you have yours like this, don't you?
Yes, Doc.
Copy this. Go to R. Copy it, go to R, and then use the command FAM1 equal to read.delim to bring the data into R. Okay. So when it is loaded, you look down there in the console and you see that the whole command will be written as blue, which means that the data is nicely loaded. If you have been able to load your data using the FAM1 command, raise your hand and let me see. If you have been able to load the data, then raise your hand and let me see. Okay. I see some two hands. Is it that the rest of you are struggling to load the data or what?
Doc, please, I for one having installed
just
the
loaded
benchmarking
myself.
yet. Okay.
You haven't installed what?
Benchmarking.
So you are now installing it or still?
Still, Doc.
Okay. Then you have to do yours later. Okay. So yeah, you've installed the data. Okay, so I'm sure those of you who have been able to do it. Now we called it farm1. If you want to see the data, just type farm1 or just highlight farm1 alone. And then you see the data down there in the console, just to fill the data. Okay. If you can see the data down there in your console, that's fine. I have command number 14 as one other means by which you can load the data. Okay. Now, do you all see the data in the console now? In yours?
Yes,
Not in mine, by yours.
Yes, sir.
Okay. So you can all see it. So we can proceed. The next thing is that if you look down there in the console, you will notice that DMU1 is the row 1. So every row has a name, and the names are 1, 2, 3, 4, 5. But the DMU names are also what? 1, 2, 3, 4, 5. Okay, the DMU names are 1, 2, 3, 4, 5. So what we want to do now is I want to convert the column for the DMU in the data frame so that they will represent the names of the row names. Okay, they will represent the names of the rows. Please, you get it?
Yes, Doc.
yes.
So watch what I'm saying. So the next time you see DMU1, it will rather be here. It will rather be replacing the number 1. DMU2 will be replacing number 2. And the command to do that is to rename the data set. Instead of as farm1, you make it farm, and then say that farm should be the farm1 without the first row, sorry, the first column. So that without the names of the row, without the first column names, so that that one will be replaced by the names of the DM. So let's run that. And once you run that, okay, you can now run the farm alone and see how it looks like. Okay, so you can see that now it has removed the names of the DMU from the data. Do you realize that?
Yes, Doc.
Move the name. Now look at the next command. The next command says, I want you now to label a new data frame. Okay, so this farm1, okay, if we want to know the row names, okay, for that farm1, what are the row names? These are the row names: DMU, DMU1, DMU2, up to DMU5. Okay, so we are going to relabel them with that. We're going to relabel the whole thing. So now look at farm1. Okay, we relabeled by replacing the names. So now when we go to the final one here, you can see that the names of the rows have been replaced by the names of the DMUs. You see what I'm seeing?
Yes, Doc.
The names of the rows have been replaced. Of course, you have all of these commands. Okay, so now we have the DMU names as the row names. This is good because it's going to help us to do a beautiful graphic. The next thing to do is to now column bind the inputs. The inputs are 2. You have X1 and X2, which are inside the data frame called farm. So what we are going to do is that we are going to column bind them. They are on their own. We're going to column bind them and represent all of them, not as X1 and X2, but as X. So that is the next command. If you want to see it, you can just type X and then have a look at it. Did I do it? Let's see. Okay, so this is it. And then now when you type X, this is it. These are representing the X variables. And then the Y, you combine all the Y's together and call them Y. Okay, and when you do that, you now get the Y variables. Of course, the Y's are 1, 1, 1, 1. Okay. Let's not bother ourselves with the prices. Okay, so we'll jump those prices. But then we are going to now plot the isoquant or the input possibility set. And we use the X1 and the X2 to do that. So we are going to rename the X1, okay, as the X1 input as X1. So we're going to rename the X1 input as S1 for purposes of drawing using this command, X1, which is inside the farm data, column X1. So I'm going to rename that. And then the X2 input, we're going to also name that as X2. Okay. So what we've done is that we are not using the Y because we would normalize the Y, which is the output. Okay. We normalize it into 1. And this is the implicit assumption of constant returns to scale. Okay. So that's it. We've been able to do that. Now, your benchmarking, we have already installed and revoked it. So we are going to use this powerful command in command number 30 here to draw the isoquant. Now, I want you to look at some few things. The command says that plot X1, X2, COL means color, and the color is blue. You can change it to red or green. The line width, LWD, is 7. You can change the number. Okay. The position is 8. The sex is the thickness. The text is true. So we want the items to be labeled. So this is going to give us a bit of a scatter plot. And then we want to give it a title, which is known as DEA isoquant. DEA isoquant. So since you have them all already, let's run this command. And then we'll look on the right in the plot, you see the plot. So on the right here, you will see that I have the plots, all of them nicely showing here. So you can see that we have the X1 and the X2. All of them have been plotted, but this plot is not looking good. Okay, so we use another scatter plot which is the next command in 31. Okay, so this command makes the scatter plot a bit small. All right. Now, there are a few things we have to note before we move on. We can change the type of the line using LTY, a line type. We can change the dimension using DRM, the color we've already mentioned, the symbol type as to whether we want the symbols to be zeros. We use box, we use number 0. If you want it to be triangle, you use 2. If you want it to be plus, you use 3. Okay. If you want it to be filled, okay, you use 4. You can use any kind of symbol for that. And then you have the position of the text, whether you want the text to be on top of it or below it, on the right of it. Okay, the command you use will indicate all of that. So we're going to use the command number 38 here, 37 here, okay, to run first the DEA and then put the text on the graph. Please, do you all have that command number 37 that I've highlighted? You have that. Okay, good. So what you are going to do is to run that command, and that command automatically constructs the frontier, the DEA frontier, and labels it. Now, if you look at the command carefully, check it. You have the orientation to be IN. IN means input orientation. You have the returns to scale to be CRS, which means we are dealing with constant returns to scale. The line width is 5, the sex is 1.25. You can change all of this. The color is now blue. Sorry, it's now red. The title is DEA frontier. So this gives us a beautiful thing. But it doesn't tell us which DMU is what. So this next command, which is text X1, X2, row names to be the names of the farm data set. Okay, so this will give us the names of the data set. Once you run that, you can see that now each of the DMUs have their names nicely written there. Now, the next thing we can do is to introduce the radial lines, okay, using this command number 39. Okay, I've done this and I just don't want to go through all of them. So this will now introduce a radial line. We've indicated that the color should be blue. You can change the color to be green. Okay, so let me just change the color to be green so that it becomes nicer. And then you want the line type to be dotted. So this is going to be zigzag lines. Okay, and this is it. So we run that, and you can see clearly that you have the green zigzag line that have drawn all the radial lines through it. This is your graph. So you can use R to generate a graph of, either in input orientation like this or in an output orientation. Now that you've done this, you can now estimate the efficiency scores. There are two kinds of efficiency scores you can estimate. You can estimate the technical efficiency under CRS, and then technical efficiency under VRS. We've already done all of this. Okay, so the next commands will do that. Because you've already installed the benchmarking, once you run the two, you get a result. For you to get a result, you go to summary TECRS. The summary TECRS is going to summarize the technical efficiency under CRS. Okay, that's going to give you the summary. So watch the summary down there in the console. There's something interesting about the summary. It tells you summary of efficiencies. And it tells you which technology is being used, which orientation is being used. It will also give you the number of fans. Okay. Imagine these are plenty, you get a summary statistics here. Then it will tell you the mean efficiency, in this case is 81%. And I will give you the ranges of some of the efficiency scores. And finally, the minimum and the maximum values, as well as the quartiles, the first and second quartile, as well as the median, all of them are given to you. This is for the technical efficiency. If you want the scores separately, you can just type TECRS to see the scores separately for each firm. And for VRS, you can do the same thing. In this case, the CRS and the VRS scores are all the same. Okay, they are all the same. So it simply means that your scale efficiency will be the 1111, because the scale efficiency is the technical efficiency CRS divided by the technical efficiency VRS. Okay. Now you can use this print command with a certain number of decimal places, okay, like I've just done. This was 3 decimal places to give you the results in a vertical order. Do the same thing for the VRS to give you the results in a vertical order. And then now you can put the VRS and the CRS together, okay, in our next command. Again, you can see that this is all 3 decimals. Okay. And sometimes you want to use the efficiency density plot to look at how they are looking like. Okay. Now I'll later teach you, okay, there's time, the importance of this density plot. Okay. Because what it does is that it's looking at not just the mean and the median, the standard deviation. Okay. It goes deeper. What the box plot might not do, it tells you the density. And because these efficiency scores are non-parametric, okay, in nature, the densities are good, they help you. So you can see that on the density, you can see that the density runs from 0 up to 3.5, and the efficiency scores are from 0 to 1. And you can see that this is showing a bit of a peak under 4, 5, and then it shows another peak under between around 0.9 thereabout. Okay. So this is just few things. But the key point of this is that there is it's based on the reflection method, okay, of Silverman. Okay. And everything under Silverman reflection method using a default window kernel are all indicated. So it's good to study about that and use that. Okay. So that is for the VRS. And that was for the CRS. Okay, the next thing is you can, of course, these are all different kinds of deficiency. Some of them I'm deepening them. You can also look at the peers of the DMUs. Look at the peers of the DMUs. So once I type peers, it will show the peers here. What does this mean? Look down there in the console. And all I'm doing is that once I do it, I'm expecting that you have also done. So if you look at peer 1, we have peer 1 and peer 2. What does that mean? So what this means is that if you look at DMU 1, okay, if you look at DMU 1, it used FEM 2 as its peer. And FEM 2 was only the peer for it. Okay, DMU 1 used FEM 2 as its peer. Let me just show you why, or partly why. Let's just go to where the results were showing. Okay, so these are the results. If you look at DMU 1, DMU 1's efficiency was what? 0.5. So that means that it was inefficient. And so it needs to copy from somebody. And the person is copying from, or the firm is copying from, is DMU 2. That's a peer. Why? We will look at DMU 2. DMU 2 is efficient, first of all. Okay, it's efficient. So it will be used as a peer. But it didn't use any other firm as a peer. So there was no peer 2. The peer 2 is not available. Now, if you look at DMU 2, DMU 2 is already efficient. So it will use itself as a peer. So it uses itself as a peer. That's the first peer used. DMU 3 is inefficient. Look down here. DMU 3 is 83%. So it's inefficient. If it's inefficient, it needs a peer. It also adopted DMU 2 as its peer. What about DMU 4? DMU 4 is inefficient. Look at it, it's inefficient. It also adopted DMU 2 as its peer. And then DMU 5, look at it, that one is already efficient. So it will choose itself as its peer. But when you look at DMU 3 and DMU 4, it was not only 2 they use as their peers, they also use 5. Okay. So here, there are 2 of them, they're using 2 peers. And when we come to interpretation, you come to appreciate it. Remember the graph. If you look at the graph, look at the graph for DMU 3. DMU 3, when you trace it down, it will hit the frontier between 2 and 5. DMU 4, when you trace it down, it will hit the frontier between 2 and 5. That's why each one of them is taking a portion of 2 and a portion of 5. But you can see that how much it uses is important. Okay, how much it uses is very important. All right, so let's continue. So you have the results there. Okay, so each one of them will have their peer. And the most important thing you should note is that the firms that are already efficient, they will choose themselves as their peers. And the firms that are not efficient, they will choose efficient firms as their peers. The next thing you can do is you can try and find out the number of peers, the number of times a particular peer was used as a peer. Okay, so this is it. So first thing is that if you look at this firm, this is firm 2, DMU 2. How many times was he used as a peer? You can see it here. It was used as a peer 4 times. Okay, and if you want to know, you can count it here. You see it that it was used as a peer 4 times. What about DMU 3? Sorry, DMU 5. DMU 5 was also used as a peer 3 times. Okay, and so that is what you see. So this command get.number.peers, it tells you how many times something was used as a peer. The last thing is the slacks. Remember, the slacks are the inputs, the leftover inputs. The leftover input. So this command, which I call SL equals to slack blah blah, it will tell you the slacks. Okay. It will tell you the slacks. And if you want to know it, just highlight it, and then you can see the slacks here. Now, if you look at each one of them, only firm 1 has a slack of 0.5. The rest have 0, 0, 0 slacks. Only firm 1. Now look at the graph. You can see that even if you project firm 1 onto the frontier, it will hit the frontier on the free disposability section. Do you realize that? it will hit the frontier on the monotonicity section, the vertical or horizontal. So in this case, on the vertical section of the graph. And so because it's hitting it, it means that it will have some non-zero slacks there. Because for it to be efficient, it will have to come down to DME2. And this is where we know that it's already exhibiting slacks. So this command will show the slacks. Now we can calculate the scale efficiency. I told you that the scale efficiency is the technical CRS over the technical VRS. So when you use this command, you can use it to calculate the scale efficiency. Okay, and then you can highlight it, run it, and show the exact number. I told you that they will all be 1, 1, 1, 1, 1, 1, especially because this is a small sample data. Now, you can use a final graph here to indicate all of the results, put all of the results together. This number 67, it will give you the CRS efficiency scores, the VRS efficiency scores, the scale efficiency score, the slack for the output and the inputs, all of them, individual slacks and the combined slacks. So let's run this very command and you see all of them. Okay. So if I'm asking you a question, this is where I'll ask you some petty questions. Okay. This is it. This is where you ask some very petty questions. If I remove some things in this thing, you should be able to see. For example, if I remove the scale efficiency, you should be able to calculate the scale efficiency, isn't it? Because you will know that the CRS divided by the VRS will give you the scale efficiency. If I remove any particular score, for example, if I remove the VRS score for FEM1, you should know it if you are already having the CRS and then the scale efficiency. So I can remove anything and then for you to calculate the others. Now, what does the true or false for the slacks mean? The true here means that that firm has a slack. That is what it means. Okay, the true, it means that that firm has a slack. The false means that that firm has no slacks. Okay, now, so if I put a value here, okay, if I put a value here and I don't write true, you should be able to know that it has a slack. So you will write true for that. Okay. You will know that it has a slack, so you will write true for that. Okay. And what is the X1? SX1. That is the input slacks. So in this very sense, the X1 doesn't have an input slack. But if you look at X2, for DMU1, it has X2's input slack or X2 slack of 0.5. And you can see that here because when you look at the graph, you will notice clearly. Let me see whether I can use this to pinpoint the graph for you. So you can look at the graph, you can see clearly that it is on the X2 section. Okay. It hits 2.5, but it must go down to 2. So there's a slack of 0.5. So you're able to use that to detect. Okay. So that is how you get a very nice data of everything that you need. Now, what about the lambdas? The lambdas. The lambdas for me are the most important things. Okay. So I'm going to talk about the lambdas briefly, and then we will now use the lambdas for other important things. Okay. The lambdas, they are very significant. So watch the lambdas. If you look at DMU1, it has no lambda. Lambda, you can see that the lambdas are L2 and L4. Why? Why was only L2 and L4, columns given as lambdas? Because FEM2 and FEM5 were the efficient firms. They were the Pareto-Koopman's efficient firms. Okay. They were the Pareto-Koopman efficient firms. And so that is why they are peers. In fact, the firms that are used are peers. They are the ones who will be having the lambdas. Okay. So they are the ones whose lambda values are going to be used. Okay. In other words, they are the ones that the others will learn from. So they are the ones whose inputs and outputs are important to any particular firm in determining that firm's efficiency. Okay. I'll be talking about that very briefly, very soon, but I just want you to know that the command lambda TCR will give you the lambda score. Okay. Will give you the lambda score. Now I want to put everything together this time with the lambda in it, okay, in this beautiful table. Because once you have it all as one, it makes the thing nicer. So this is it. This is a complete table you may have. This time the table has everything, everything. If I delete some of them, you should be able to calculate them, everything. So we need to be able to use these things. If I decide, and this is very important, if I decide that some of the efficiency scores, I'm going to delete them. I'm going to delete some of the efficiency scores so that you find them. Okay, so that you find them. There are so many ways you can find them. There are so many ways. Okay, so that is the essence of the exercise we are going to do now. So for now, I'm going to take you to the table. I've gone through everything that you are seeing here in the lecture slides. I've gone through all of this. I showed these results. I showed efficiency density graphs. I've spoken about the PS and all of that. And these PS I showed you in the results. Okay, this is it. I showed you the PS and all of that. Now, there's one thing that you should know, and this is important, so I want to make that clear. Efficient firms may consider themselves to be their own peers, and we've said that. The word benchmarks is the same as targets for our purpose. So when you see the word benchmarks, it's the same as targets. So let me ask you, I think I told Diana to walk you through that. What is the difference between peers and targets? What is the difference between a peer and a target? Who can tell me? What is the difference between a peer and a target? Okay, Stephen.
Okay, look, I think all peers are fully efficient, but not all targets are fully efficient.
Say that again.
I say all peers are fully efficient firms, but not all targets are fully efficient.
No, not really. Not really. That is not a clear difference. What is the main difference between peers and targets? Any other? Peers and targets. Now remember that the targets are hypothetical DMUs. They can be anywhere. The targets can be where the peers are. So when you trace the thing to hit the boundary of the production possibility set, it can hit a point where there's the peer. Peers are real DMUs, real. Targets are any point on the frontier, which can be real DMUs or artificial DMUs, or what we call virtual DMUs. But the main difference between peers and targets is that all peers are targets, but not all targets are peers. This is important. Do you get it, or I should go over it? All
No,
peers.
please repeat.
Sorry?
Okay, I was saying please repeat.
Okay,
All right.
I will repeat by using even a graph to explain it to you. Okay, let's go back and use this graph, for example. If you look at this DMU1, it's a real DMU. Now the firms that are on the frontier here, okay. So let's take, for example, there are some of the firms like this one, okay, this one here. Now this firm, DMU2, is a real DMU, isn't it? It's a real DMU. Now DMU5 is also a real DMU. I can trace a certain DMU that will hit 5. it will hit 5, and 5 becomes its target because it's on the frontier. But that 5 also happens to be a real DMU because it's a peer. It's a peer. For you to be a peer, you must be real. You must be real DMU. However, I can have another firm like DMU4. It's not efficient. If I trace it, it will hit the boundary at a point. What point? At a point here. Okay. It will hit the boundary at that point, but at that point, there is no real DMU there. But there is an invisible, virtual, or artificial, or hypothetical DMU there. You understand? And any portion of the boundary of the frontier, any portion represents that hypothetical, virtual DMU, including even where real DMUs are. So that's why we say that anytime you are a peer, you are automatically a virtual, or you are automatically a benchmark. Now, where the thing hits is a benchmark. Where the thing hits is a benchmark. And it can hit here, okay? It can hit there, it can hit there, and it can also hit where there's a real DMU. It can also hit there, okay? It can hit here where there's a real DMU. So a target is where, you know, an inefficient firms will be projected onto on the frontier. But then the peers are those real DMUs on the frontier. So as long as you are a peer, you are automatically a target to somebody, to an invisible any firm. But it doesn't necessarily mean that you are, if you're a target, you're a peer. Because if you look at this section, 3 prime here is a target for 3. Okay, 3 prime is a target for DMU3. But that portion here is not a real DMU. Okay? It's not a real DMU because the real DMUs are the ones that are actually labeled with peers. Does it make sense now?
Yes, sir.
Perfect. Perfect. So that is what we want to be able to understand when it comes to real DMUs, and then and peers and targets. And of course, the targets are also called benchmarks in this context. Now, the peers are also called role models. So it's the same name. Okay. So when you look at DMU1, DMU1 was inefficient. Okay. DMU1 was not efficient. Look at it. DMU1 is inefficient. Who will be his peer? His peer will be the one it will be closest to if he hits the target. So if he hits the target, it will be closest to DMU2. So DMU2 becomes the peer for DMU1. And that's a point being indicated there, that the role model or the peer for DMU1 is DMU2. But the role model for DMU2 is itself. Why so? Because it's already efficient and it's on the boundary. Okay. All right. We have already spoken about slacks and then scale efficiency. And then we've spoken about lambdas. I want to now explain something quickly about lambdas. Lambdas, we've already said, are the weight or the importance of the peers. This is important. The word is the weight of the peers for each firm. Is the importance of the peers for each firm. You see, the efficiency of every firm is being measured. And every firm has a peer. Even if you're efficient, you will have what? A peer. Even if you're efficient. Even if you're efficient, you will have a peer. And so because you have a peer, it is important for you to understand that once you are a peer to somebody, you will have a lambda. Once you are a peer to another firm, you will have a lambda. Okay, so the lambda now becomes the weight of the peers for the firm. So when we calculated these weights, you can see, let's go to the graph. You can see that the lambda for DME3, okay, This is it. So look at DME3. This is DME3. Its lambda is 0.667. But that lambda is for a peer called FEM2. So this is coming from DME2 because DME2 was a peer for DME3. But it wasn't only that, it was also a peer for DME5. If you can remember, when you trace the DME3, it will hit the boundary between DME2 and DME5. And that is why so what this means is that DME3, for it to be efficient, is putting 67%, importance on DME2 and putting 33% importance on DME5. That's what it means. Okay, it's putting more weight. As far as DME3 is concerned, DMU2 will help him to be very efficient than DMU5, but it doesn't rule out that the fact that DMU5 will also help him. But DMU2 will help him by more. So there's more weight attached. So in other words, what it means is that for DMU3 to be efficient, for DMU3 to be efficient, it will have to do something using these weights of DMU. For DMU3 to be efficient, it will have to do something using these weights of DMU2 and 5, using the 67% and the 33%. And then working that out with the input, its input, so that it becomes efficient. And we are going to do that very soon. Okay? We're going to do that. And that is what is known as target setting. Target setting is a very important thing. Okay, but for now, let me just go back to the point. So the lambda for DME3 is 0.667, and the lambda for DME2, okay, is 0.33. And if you look at it, the lambda for DME3 is 67, but which is from DME2. So in other words, it's putting 67 weight on DME2 and then 33% weight on DME5. Now, if you look at DME4, it is also an inefficient firm, and its lambdas have also been indicated. Now, you can see that DME4 is putting more weight on 5, on DME5. Why? Because when you look at the tracing, you see that the target tracing, it is closer towards 5 than towards 2. Unlike for DME3. DME3, its target tracing is closer to DME2 than DME5. Okay. Now let's go back to our table. Suppose I have deleted the efficiency score for DME3. Okay. Suppose I have deleted the efficiency score of DME3. And I've also even deleted the VRS score. Okay, both the VRS and the CR, I've deleted all of them. How do you find the efficiency score? There are two ways you can find. How do you find the target? How do you find a target? How do you find the target of DME3? If I had not deleted anything, by the way, if I had not deleted anything, how do you find the target? Well, one way you can find the target is using this efficiency score. Another way you can find the target is using these lambdas for that DM. How do you do that? Now, let's see. You can use the lambda values, which is coming from DME2 and DME5. We just spotted that. The lambda values of DMU3, you can use that to find the target or the benchmark for DMU3. How? So if I tell you to find a target for DMU3 and I've given you these lambdas, you should be able to find that. How? How do you do that? Well, first of all, understand that the word virtual, which I told you that is the name for the hypothetical point, That virtual is made up of the weight multiplied by the variable input or the output. So the weight, remember the weight is the lambda. So that can give us the virtual. Okay. Now, so if I want to find the target for DMU3, it's input 1. Because remember, as it stands, the input X1 for DMU3 and the input X2 for DMU3, they are not the right input. They are not the proper. Look at it. The inputs are 2 and 2. And those inputs are not correct. Why? Well, they are not correct because if they were, that firm would have been what? Efficient. It would have been efficient. But because they are not correct, the firm now is not efficient. So what should the input be? That's a question. Now, if you know that this is an input orientation, so we got to reduce the input. Reduce the input from where to where? Well, we know from 2, but we don't know to where. So we need to reduce the input X1 from 2. And we need to reduce the input X22 from 2. And we are going to use these lambdas to help us know the reduction capacity. There is I developed a small formula that you can use. How do you do that? Well, first you need the lambdas. What lambdas? The lambdas that you have, the lambda 2 for DMU3, and then the lambda 5 for DMU3, lambda 2 for DMU2, and the lambda 5 for that DMU3. You need those 2 lambdas. So for the lambda 2, you're going to multiply it by the DMU2's input. So you know that the input for DMU2, the input is what? 2. You multiply that input 2 by this lambda, 0.667. Then you multiply that same input 2, okay, by this second lambda. And then you add them, as many lambdas as possible. Okay, and that's what I've done there. So multiply the lambda by the input plus the DMU5's lambda by the input. Oh, sorry. Let me just go over it again. Otherwise, you get confused. So you multiply the DMU2's input. Okay. You multiply the lambda, okay, for that DMU5. Sorry, for that DMU2. Okay. So let's go back. You multiply this lambda 0.67. Okay. This lambda 0.67 by, because it's from 2, by the input 1 of DMU2 here, input 1 of DMU2. So 1 times 0.67. And then you multiply lambda, this lambda 0.333 by the same input of DMU3. Sorry, DMU5. And that input for DMU5 is 3. Okay, so you are using the input, their role models, their inputs to now calculate the target for this very DMU who is suffering. Okay, so you take, first of all, you take the lambda, and this is it, we are calculating the target for DMU3. You take the lambda, which is coming from 2, multiply by the input of 2, which is 1. Plus, you take the lambda, which is coming from 5, multiply by the input of 5. And then you add them. Now, why are we taking the 2 of them? We are taking the 2 of them because it was saying that the 2 of them help him to be efficient. And when you do that, that is going to give you 1.67 approximately. So you remember we said that the inputs of DMU3 are 2 and what? 2 and 2. So for the first input, you are reducing it from 2 to 1.67. That's what it means. What about for the second input? Let's go back. For the second input, if you have the data, okay, you're going to use the same individual, okay, for the second input. But you will not use the first input of the firms, of the peers. You use the second input of the peers. So you are still going to multiply 0.66 here times, this time not the DMU2, it's input 1, but it's input 2. Okay. Then you multiply the 0.33, which is coming from DMU5. You multiply it by DMU5's input 2, which is 1. So you do 0.66 times 2, and then 0.33 times 1. And when you add these together, that will tell you how much you got to reduce the input of DMU3, which is 2, to where? To that number, the answer you get. Well, it happens to be that that one too happens to be 1.67. So you take the lambdas, multiply by that. So you can use the lambdas in R together with the inputs of that peer or the outputs of that peer, if it is output you are dealing with, to find that target input. If it was output orientation, to find that target output. You can use the lambdas together with the peers inputs to find the target of any inefficient term. Or you can use the lambdas together with the peers output, if it is output orientation, to find the target for an inefficient firm. Do you get it? I hope you followed. Do you follow? Or is a bit, yeah. You should be able to.
Sir.
So the one and the 3 that you see here, the 1 and the 3, and then the 2 and the 1, these are the inputs of the peers or the role models for that particular thing. Now, if I tell you to tell me the peers of DMU2, DMU2's peers, if you look at it, they are 0. Okay. Watch the graph. Okay. So if you look at it, DMU2, okay, all the inputs were put on what? Were put on lambda 1. So in other words, he's putting all the weight on itself. So you multiply that 1, which is 1, by the peers, but the peer is itself. So you multiply that 1 by itself, which is 1, and you multiply that 1 by itself, which is 2. Okay, so you can see that you arrive at the original. So it means that where the inputs and outputs is having now are the correct inputs and outputs. You shouldn't touch it. It's already on the frontier. Okay. And so the lambdas can really help you to arrive at your final destination. Now, finally, there's one thing that R can do, and that is calculating the input saved, the inputs that could be saved. You see, right now, we have realized that some inputs were being used that were not supposed to be used. But if all the firms were efficient, okay, how much input could be saved? The input saving potential for each firm can be calculated as 1 minus the efficiency scores, or then multiplied by that very input. Okay. And then you can do it for all the firms, the total input saved for the entire industry. So we've saved, in this case, when you go through this R command, it will tell you that we've saved 5.6, inputs. If all the firms were efficient. So this helps you to be able to determine the aggregated efficiency. That if we are to help everybody to be efficient, this is how much input can be saved. And of course, we can convert that into monetary value to know how much resources are being wasted as a result of inefficiency. Okay, and of course, you can convert that number into a percentage to get it in a better way. So, ladies and gentlemen, that is how you analyze this very, thing. But the most important thing is that if you are given this, you should be able to find some few things. Okay. Now let me show you something that we calculated here. Okay. Suppose I tell you that the target, watch it carefully. The target for input 1 is 1.67. Okay. The target for input 1 for 1.67. In fact, I won't even say that. I think what I would say is that calculate the target. Okay, using these lambdas, calculate the target for that. But you see, there's another way you can easily calculate the target. There's another beautiful way for calculating the target. Let me show you that, even though I didn't mention it. Okay. Now look at the efficiency score. You can use the efficiency score and multiply it by that very input, its original score, to get the actual target. That's easy. So take 0.833 and multiply it by the inefficient firms' input themselves. That will tell you straight away the target. That's another way of finding the target. So 0.833, if you take a calculator, and then you do 0.833, okay, and then you multiply 0.833. I'm doing it, so I just hope that you are also doing it. 0.833 by 2, you get the same 1.67. Okay, so you can use the efficiency score to get to the target, but I want you to learn both, because I will never let you use an easy way alone. You got to know all that means, because it helps you to understand. So there are two ways of arriving at the target. One, using the efficiency scores here, multiplying it by the inefficient firms variables, one by one, and then you will know the target, or using the lambdas. Okay. The lambda one is important because you are learning from the peers. And so that is why I would love to do that as well. So that brings us to the end of how to do the basic efficiency score on that. Now, what we haven't done is that we have not brought bootstrapping into it. We've not calculated other things, but this is basic efficiency and how to find all of them.